A polymer is a large molecule, or macromolecule, composed of many repeated subunits. Because of the broad range of properties, both synthetic and natural polymers play an essential and ubiquitous role in everyday life. Polymers range from familiar synthetic plastics such as polystyrene to natural biopolymers such as DNA and proteins that are fundamental to biological structure and function. Polymers, both natural and synthetic, are created via polymerization of many small molecules, known as monomers. Their consequently large molecular mass relative to small molecule compounds produces unique physical properties, including toughness, viscoelasticity, and a tendency to form glasses and semi-crystalline structures rather than crystals. The term polymer derives from the ancient Greek word piomicron lambda upsilon sigma and mu epsilon rho omicron sigma, and refers to a molecule whose structure is composed of multiple repeating units, from which originates a characteristic of high relative molecular mass and attendant properties. The units composing polymers derive, actually or conceptually, from molecules of low relative molecular mass. The term was coined in 1833 by John Jacob Berzelius, though with a definition distinct from the modern IUPAC definition. The modern concept of polymers as covalently bonded macromolecular structures was proposed in 1920 by Hermann Staudinger, who spent the next decade finding experimental evidence for this hypothesis. Polymers are studied in the fields of biophysics and macromolecular science, and polymer science. Historically, products arising from the linkage of repeating units by covalent chemical bonds have been the primary focus of polymer science. Emerging important areas of the science now focus on non-covalent links. Polyisoprene of latex rubber and the polystyrene of styrofoam are examples of polymeric natural, biological and synthetic polymers, respectively. In biological contexts, essentially all biological macromolecules, i.e., proteins, nucleic acids, and polysaccharides, are purely polymeric, or are composed in large part of polymeric components, e.g., isoprenylated lipid-modified glycoproteins, where small lipidic molecules and oligosaccharide modifications occur on the polyamide backbone of the protein. The simplest theoretical models for polymers are ideal chains. Common examples. Polymers are of two types. Natural polymeric materials such as shellac, amber, wool, silk and natural rubber have been used for centuries. A variety of other natural polymers exist such as cellulose, which is the main constituent of wood and paper. The list of synthetic polymers includes synthetic rubber, phenol formaldehyde resin, neoprene, nylon, polyvinyl chloride, polystyrene, polyethylene, polypropylene, polyacrylonitrile, PVB, silicone, and many more. Most commonly, the continuously linked backbone of a polymer used for the preparation of plastics consists mainly of carbon atoms. A simple example is polyethylene, whose repeating unit is based on ethylene monomer. However, other structures do exist. For example, elements such as silicon form familiar materials such as silicones, examples being siliputty and waterproof plumbing sealant. Oxygen is also commonly present in polymer backbones, such as those of polyethylene glycol, polysaccharides, and DNA. Polymer synthesis. Polymerization is the process of combining many small molecules known as monomers into a covalently bonded chain or network. During the polymerization process, some chemical groups may be lost from each monomer. This is the case, for example, in the polymerization of PET polyester. The monomers are terephthalic acid and ethylene glycol, but the repeating unit is OCC6H4COOCH2CH2O, which corresponds to the combination of the two monomers with the loss of two water molecules. The distinct piece of each monomer that is incorporated into the polymer is known as a repeat unit, a monomer residue. Laboratory synthetic methods are generally divided into two categories: step growth polymerization and chain growth polymerization. The essential difference between the two is that in chain growth polymerization, monomers are added to the chain one at a time only, such as in polyethylene, whereas in step growth polymerization, chains of monomers may combine with one another directly, such as in polyester. However, some newer methods such as plasma polymerization do not fit neatly into either category. Synthetic polymerization reactions may be carried out with or without a catalyst. Laboratory synthesis of biopolymers, especially of proteins, is an area of intensive research. Biological synthesis. There are three main classes of biopolymers: polysaccharides, polypeptides, and polynucleotides. In living cells, they may be synthesized by enzyme-mediated processes, such as the formation of DNA catalyzed by DNA polymerase. The synthesis of proteins involves multiple enzyme-mediated processes to transcribe genetic information from the DNA to RNA and subsequently translate that information to synthesize the specified protein from amino acids. The protein may be modified further following translation in order to provide appropriate structure and functioning. There are other biopolymers such as rubber, suberin, melanin and lignin. Modification of natural polymers. Naturally occurring polymers such as cotton, starch and rubber were familiar materials for years before synthetic polymers such as polyethylene and perspex appeared on the market. Many commercially important polymers are synthesized by chemical modification of naturally occurring polymers. Prominent examples include the reaction of nitric acid and cellulose to form nitrocellulose and the formation of vulcanized rubber by heating natural rubber in the presence of sulfur. Ways in which polymers can be modified include oxidation, cross-linking and end-capping, especially in the production of polymers. The gas separation by membranes has acquired increasing importance in the petrochemical industry and is now a relatively well-established unit. Operation. The process of polymer degassing is necessary to suit polymer for extrusion and pelletizing, increasing safety, environmental, and product quality aspects. Nitrogen is generally used for this purpose, resulting in a vent gas primarily composed of monomers and nitrogen. Standardized polymer nomenclature. There are multiple conventions for naming polymer substances. Many commonly used polymers, such as those found in consumer products, are referred to by a common or trivial name. The trivial name is assigned based on historical precedent or popular usage rather than a standardized naming convention. Both the American Chemical Society and IUPAC have proposed standardized naming conventions. The ACS and IUPAC conventions are similar but not identical. Examples of the differences between the various naming conventions are given in the table below. In both standardized conventions, the polymers' names are intended to reflect the monomer from which they are synthesized rather than the precise nature of the repeating subunit. For example, the polymer synthesized from the simple alkene ethene is called polyethylene, retaining the -ene suffix even though the double bond is removed during the polymerization process. Polymer characterization. The characterization of a polymer requires several parameters which need to be specified. This is because a polymer actually consists of a statistical distribution of chains of varying lengths, and each chain consists of monomer residues which affect its properties. A variety of lab techniques are used to determine the properties of polymers. Techniques such as wide-angle X-ray scattering, small-angle X-ray scattering, and small-angle neutron scattering are used to determine the crystalline structure of polymers. Gel permeation chromatography is used to determine the number, average molecular weight, average molecular weight, and polydispersity. FDII, Raman and NMR can be used to determine composition. Thermal properties such as the glass transition temperature and melting point can be determined by differential scanning, calorimetry, and dynamic mechanical analysis. Pyrolysis followed by analysis of the fragments is one more technique for determining the possible structure of the polymer. Thermogravimetry is a useful technique to evaluate the thermal stability of the polymer. Detailed analysis of TG curves also allows to know a bit of the phase segregation in polymers. Rheological properties are also commonly used to help determine molecular architecture as well as to understand how the polymer will process. Through measurements of the polymer in the melt phase. Another polymer characterization technique is automatic continuous online monitoring of polymerization reactions, which provides real-time characterization of polymerization reactions. It can be used as an analytical method in R&D, as a tool for reaction optimization at the bench and pilot plant level, and eventually, for feedback control of full-scale reactors. ACOMP measures in a model-independent fashion the evolution of average molar mass and intrinsic viscosity, monomer conversion kinetics, and, in the case of copolymers, also the average composition drift and distribution. It is applicable in the areas of free radical and controlled radical homo and copolymerization, polyelectrolyte synthesis, heterogeneous phase reactions, including emulsion polymerization, adaptation to batch and continuous reactors, and modifications of polymers. Polymer degradation. Polymer degradation is a change in the properties, tensile strength, color, shape, or molecular weight of a polymer, a polymer-based product, under the influence of one or more environmental factors, such as heat, light, chemicals, and, in some cases, galvanic action. It is often due to the scission of polymer chain bonds via hydrolysis, leading to a decrease in the molecular mass of the polymer. Although such changes are frequently undesirable in some cases, such as biodegradation and recycling, they may be intended to prevent environmental pollution. Degradation can also be useful in biomedical settings. For example, a copolymer of polylactic acid and polyglycolic acid is employed in hydrolyzable stitches that slowly degrade after they are applied to a wound. The susceptibility of a polymer to degradation depends on its structure. Epoxies and chains containing aromatic functionalities are especially susceptible to UV degradation, while polyesters are susceptible to degradation by hydrolysis, while polymers containing an unsaturated backbone are especially susceptible to ozone cracking. Carbon-based polymers are more susceptible to thermal degradation than inorganic polymers such as polydimethylsiloxane, and therefore not ideal for most high-temperature applications. High-temperature matrices such as bismaleimides, condensation polyamides, triazines containing ring, and blends thereof are susceptible to polymer degradation in the form of galvanic corrosion when bare carbon fiber reinforced polymer CFRP is in contact with an active metal such as aluminium in saltwater environments. The degradation of polymers to form smaller molecules may proceed by random scission or specific scission. The degradation of polyethylene occurs by random scission, a random breakage of the bonds that hold the atoms of the polymer together. When heated above 450 degrees Celsius, polyethylene degrades to form a mixture of hydrogen hydrocarbons. Other polymers, such as poly, undergo specific chain scission with breakage occurring only at the ends. They literally unzip or depolymerize back to the constituent monomer. The sorting of polymer waste for recycling purposes may be facilitated by the use of the resin identification codes developed by the Society of the Plastics Industry to identify the type of plastic product failure in a finished product. Such a change is to be prevented or delayed. Failure of safety-critical polymer components can cause serious accidents, such as fire in the case of cracked and degraded polymer fuel lines. Chlorine-induced cracking of acetyl resin plumbing joints and polybutylene pipes has caused many serious floods in domestic properties, especially in the USA in the 1990s. Traces of chlorine in the water supply attacked vulnerable polymers in the plastic plumbing, a problem which occurs faster if any of the parts have been poorly extruded or injection molded. Attack of the acetyl joint occurred because of faulty molding, leading to cracking along the threads of the fitting, which is a serious stress concentration. Polymer oxidation has caused accidents involving medical devices. One of the oldest known failure modes is ozone cracking caused by chain scission when ozone gas attacks susceptible elastomers, such as natural rubber and nitrile rubber. They possess double bonds in the repeat units which are cleaved during ozonolysis. Cracks in fuel lines can penetrate the bore of the tube and cause fuel leakage. If cracking occurs in the engine compartment, electric sparks can ignite the gasoline and can cause a serious fire. In medical use, degradation of polymers can lead to changes of physical and chemical characteristics of implantable devices. Fuel lines can also be attacked by another form of degradation, hydrolysis. Nylon 6,6 is susceptible to acid hydrolysis, and in one accident, a fractured fuel line led to a spillage of diesel into the road. If diesel fuel leaks onto the road, accidents to following cars can be caused by the slippery nature of the deposit, which is like black ice. Bibliography. Cowie, J.M.G. Polymers, Chemistry and Physics of Modern Material. Glasgow, Blackie. ISBN 0-412-03121-3. Ezran, Maya. Plastics Failure Guide, Cause and Prevention. Munich, New York, Hansa Publishers. Cincinnati, ISBN 1-56990-1848. Hall, Christopher. Polymer Materials. London, New York, Macmillan. ISBN 0-333-46379-X. Lewis, P.R. Reynolds, Ken, Gag, Colin. Forensic Materials Engineering, Case 2D. Boca Raton, CRC Press. ISBN 0-8493-11829. Wright, David C. Environmental Stress Cracking of Plastics. RAPRA. ISBN 9781859570647. Louis, Peter Rees. Forensic Polymer Engineering, Why Polymer Products Fail in Service. Cambridge. Woodhead Publishing. ISBN 1845691857. Workman, Jerome. Workman, Jerry. Handbook of Organic Compounds. Near IR, Raman, New Vivis Spectra featuring polymers and surfactants. San Diego Academic Press. ISBN 9780127635606.